be going out to some other social media platforms as well, Facebook, Twitter, and YouTube. Though it is probably best, if you do want to follow these contents, these broadcasts, the best way to do it is on the apps platform. Just a link at the top. That way you get just a better, more integrated experience, comments and things work, but you can watch it on any of the others. So what we're going to talk about today is the question why sometimes different types of insects all look rather similar to one another, and why that might be. We'll particularly look at some ones that look sort of bee-like, or some of them indeed will be bees today, just to illustrate various points, but we'll look at some other examples as well. And we'll have a talk about that, have a look at some specimens, some examples from the collection, and one or two living examples as well that I'm holding on to. And yeah, that's what we'll talk about. So one of the things people might have noticed is there are quite a lot of insects that have a similar sort of pattern of yellowy or orangey and black stripes. Your typical bee pattern, if you want. And I'll show you some examples of these in a moment. Which we'll have a look at down here. So what we've got down here, this is your honeybee, a standard, the bee that makes the honey for you, that lives in hives and so on. And you can see this bee's patterns in general is it's sort of yellow with black stripes, or I suppose black with yellow stripes, depending on which way you want to say it. And that perhaps is obvious enough. That's what a bee looks like. Most people know what a honeybee looks like. They're a remarkably common species because we humans have essentially domesticated them, moved them around, and have put them everywhere. But honeybee, so black and yellow stripes. So it's a type of bee, type of Hymenopteron. And of course, one of the things people know about honeybees is they can sting you. If you bother them, if you try to pick one up, it can hurt you. And if you're a predator that was looking to eat this honeybee, if you tried to grab it, you might well get stung, you might well get hurt. That might be a bad thing. And that's important, and we'll come to that in a minute. But there are other types of bee, and let's just go and have a look at this one up here. Again, this is a bumblebee. This is buff-tailed bumblebee. Let me bring it a bit closer. You can actually see three. It's the one in the middle of the screen anyway. Is buff-tailed bumblebee. It's quite a large bumblebee. And this is a queen, a female. But again, you can see it's got that sort of pattern we were seeing on the honeybee of black and orangey yellow stripes. And again, this is an insect that has a sting, that can defend itself by stinging. And again, if you're a predator, that's a problem. If you try to eat this, if you're a bird or something, a little mammal, something that's trying to eat this bee, well, it's lots of tasty protein, but you'll get stung, and that may well hurt. And then another of the bumblebees, this is Bombus hypnorum, the tree bumblebee. A fairly recent colonist to Britain, this bee actually. It's not been present in the country for that long. It seemed to arrive by natural means. It doesn't seem to be something we've introduced as humans, although to some extent you can never quite tell because there's so much human interaction. But again, you've got this sort of pattern, orange, black coloration. Perhaps not quite as stripy, this one, but no, there's orange, black, and its abdomen's a bit drooped, but you can see the abdomen's got a paler tail to it. And again, this is a creature that can sting itself, can sting other things that are trying to predate it. And then the final one of this little group I'll show you, and these are preserved in alcohol here. And these are an invasive species accidentally introduced to Britain and to Europe by people. And they are called Vespula Veluta, or the Asian hornet. They're quite a large, quite a pestiferous species, or they can be. They're certainly a pest to commercial bee farming, and beekeepers dislike them. It's less evidence that they're a major threat to our native species, but they haven't been here in Britain in large numbers, so potentially there. But again, you've got that sort of shape, that sort of black and yellowy-orange striped pattern. So what's going on there? Why are these things got this similar pattern? You could think, well, there's no particular reason they should have those similar patterns. They've all got their stings, they've all got their ways of defending themselves, but they're different insects, they're doing different things. So, why are they all orange and black striped? And the thinking there, the idea there, is that there's good evolutionary pressure for this. So if you think about the birds and such like that might be going to predate on those insects, they might be going to eat those insects, they will learn as they're growing up, when they try to eat something, that they sometimes get a nasty sting. And if they learn that they get a nasty sting, they'll want to avoid the thing that gave them a nasty sting next time. They'll want to stick to stuff that they can eat that's nice and tasty, but that doesn't injure them, doesn't hurt them. So if you've something that's got a nasty sting, you've got a way of defending yourself, and a sting would be an example here, then you can, that insect, wants is the wrong word when you talk about evolution, but the selective pressure, an insect which demonstrates that, which signals it's harmful, is less likely to be eaten, because the birds will have learned from trying to eat a different one that that's bad, that that's something that is harmful, that is going to damage you. Now that's, in some makes sense, so that's why to some extent you might expect something that is harmful, that can sting, or that defends itself in some other way that's harmful to the predator, to advertise that fact, to tell the predator, because there's no point, from the point of view of the insect itself, being killed but fortunately injuring its predator on the way. It needs to avoid being killed. So that signal, the birds learn yellow and black stripe is a problem. They try to eat a honeybee, they think, oh, I've eaten a honeybee, I've got stung, yellow and black striped honeybee, don't like them, not going to eat one of them again. Well, if that's what's going on, of course, so if a bird has tried to eat a honeybee like this and has learned yellow and black stripes are dangerous, then this bumblebee, which has also got its yellow and black stripes, gets an advantage of having the same pattern, because the same learning that the bird's done says avoid this insect as well. So there is a good selective pressure on these things to look like each other, to try and look similar to one another, and therefore benefit from each other's signals. So that would be the case that effectively the insects work together. I'm just trying to look something up as I'm talking. The insects they don't work together in a formal intellectual sense, but the evolutionary pressure means that it's good for them to all have the same way of signaling, I'm dangerous, don't try and eat me, because they all benefit from each other's ability to signal. I'm just looking something up, just give me a second. And that can extend to other things beyond. All the things we looked at there were Hymenoptera, were insects in the bees and wasps group. That's what we were looking at so far. But similar colour patterns exist in some other insects. I haven't got examples of all of them, or many of them, which are similar. So I'll show you a picture in this rather nice field guide. If you've got any interest in studying Lepidoptera in the United Kingdom, this is one of the books you really need to buy for yourself. But this caterpillar at the top right here, the fox moth caterpillar, a young larva of it, that has hairs on it which can be a bit irritating, can be quite harmful to anything that tries to eat it. And it's got that black and yellow patternation. So that is probably, like these wasps, a similar lesson, a similar message to things that want to eat it. Black and yellow, stay away, I'll do you harm if you try and eat me. So lots of other groups. But the point here is these things all benefit from each other's patterns. So this honeybee benefits from this caterpillar saying, I'm poisonous, I'm black and yellow. This caterpillar benefits from this honeybee having that pattern, and so forth for the other bees and the hornets and so on. They all benefit from each other's colours and each other's patterns. And that form of mimicry, that form where the insects mimic, they look like each other, they to some extent pretend to be each other or partially look like each other, is often referred to as Mullerian mimicry. I'll come to Batesian in a minute. Mullerian mimicry. And it's an evolutionary process where it's in the interest of all these insects to signal that they're dangerous in the same way, because the things that they're signalling to, the birds, the mammals, the things that might want to eat them, learn the signal once and then everyone's protected. So if everybody else is saying, I'm black and yellow, so I'm dangerous, so stay away from me, an insect which tried to signal it was dangerous by being green and red might well get eaten a lot more because things haven't learned black and yellow, dangerous, stay away. So there's strong evolutionary selective pressure on things to match that same colour pattern. And so the term for that gets referred to as Mullerian mimicry. I think I've also heard it referred to as honest mimicry. Honest because the things that are doing it genuinely are harmful, so they're telling the truth about what they're like. I've sort of heard it called cooperative mimicry. I think that's a bit of an evolutionary unfair term, but in some sense, the different types of insect are cooperating together to teach the predators the same lesson: black and yellow, dangerous, don't eat me. So that's one type of mimicry. But then we've got some other insects, and I'll show you 3 examples. Again, we'll just turn around and we'll start here. This is a type of fly. It's called Bombelius Major, or a bee fly. It looks very bumblebee-like. It's got a bit of that black, yellow, stripy patternation going on, and it's completely harmless. It can't sting you, it can't bite you, it can't hurt you. If you're a bird looking for something tasty to eat, this would be a lovely, tasty bit of protein for you. But it's got some of the pattern going on that we saw on the other insects, which could sting you. And then if we come down here, this is a type of moth. Now, this is one of the clearwing moths. This one in particular is called six-belted clearwing, or Bombicia ichneumeiformis. And when we're talking about things mimicking each other, this one's name is really reflecting that. So both bits of its scientific name, Bombicia refers to, I think it's Bembus, a type of sand wasp, because somebody thought it looked a bit like a sand wasp, another type of insect. And ichneumeiformis, ichneumons are another type of Hymenoptera, type of wasp, and people thought it looked a bit like that. But this is a moth. This is not a wasp. It's a moth pretending to be a wasp, It's even lost most of the scales on its wings, so it's got transparent wings. But it's got that black and white stripy pattern. And again, this is a completely harmless insect. It can't sting, it's not toxic, it's not got harmful hairs. So it's, again, something, if you're a bird, you want to eat this, and it's not going to do you any harm, and that's just lovely, and you want to chew down on it or bite down on it and eat it. And then, you may not be able to see this, in here, a living example for once, is a hoverfly. I haven't identified this to species level. Hoverflies are Syrphidae, Syrphidae. It's just flying on the meadow as I was coming over here to do this. And in the brief moment it's in focus, you might be able to see, again, that's got this black and white stripy pattern going on. And again, that's a harmless insect. It can't sting, can't bite, not toxic, not got harmful hairs on it. If you're a bird, you want to eat this. But those things that we've just looked at, they all had a very similar sort of black and yellow stripy pattern to the ones we were looking at which could sting. And this gets referred to as Batesian mimicry. And what's going on here is these things are, to use human language, cheating. They are putting on the colours of the dangerous stingy insect, and they are saying, I can sting you. But they can't. They're cheating. But that's in their interest. That's good for them, because if they are giving that signal, the birds aren't going to eat them. The birds don't know they're being lied to. The birds have learned black and yellow stripy, dangerous, don't eat that, it'll sting, it'll hurt. So when they see one of these, they think, black and yellow stripy, I'll stay away from him. Stay away from her. So these insects are, if you want, cheating or taking advantage of the others. And they've got the advantage of the protection that comes from being thought to be dangerous without having to invest any of their biological processes or any of their time in producing, hi Betty, they don't invest any of their own biology in producing a sting or producing a poison or producing a toxin. So they get the advantage of the protection and they don't incur the cost. So if that's going on, you might think, well, why don't all insects just turn black and yellow and then none of them will get eaten and the entire world will be full of insects? Well, that goes back to what we were talking about before. When we were talking about the insects that do have a sting, that do have a way of defending themselves, that use this colour pattern, we talked about the birds, the predators, the mammals and so on that want to eat them, learning about that, discovering that. So they might not have encountered a stripy insect before, so they'll try the first one and they'll get stung and they'll learn, maybe not, maybe they'll try a few more, but eventually they'll get the message, stripy, stingy, bad. But what if you had lots and lots of these ones that are cheating? So what if you had lots and lots and lots of these six-belted clearwing moths flying around? As many, maybe, huge numbers of them, similar numbers to the numbers you're getting of, say, these honeybees or these bumblebees. Well, if there are lots and lots of these insects, then the birds are probably going to encounter lots more of these, and they might well learn it's worth the risk of having a bite at that yellow and black thing, because it's probably one of these yummy, harmless, pretendy ones, and not one of these. So in general, the things that are doing this Batesian mimicry, that are cheating if you want, that are pretending that they are threatening in some way, but aren't, can't become too common relative to the things they're pretending to be. Because if these become too common, if this became too common, it's worth a bird having a bite of that, of a yellow and black striped thing, even though every so often it'll grab one of these and it'll get a nasty surprise. But as long as these are the most common, as long as these sort of things are the most common that can harm you, it's not worth the birds having a go. It's not worth them trying. It's not all birds that do it. I have to keep using birds as examples. But it's not worth the predators having a go, because they'll probably get one of these nasty things. And the chance that they do get one of these things they can eat safely is pretty low. Now, a thought that struck me, and this is a little bit beyond what I know, I'll probably go and try and look this one up a bit later, is amongst these Hymenoptera and these bees here, it's only the females that can sting. So it's only the females that are actually harmful to birds. The sting in these insects is a modified egg layer, ovipositor. It's a modified part of the female reproductive system, effectively. So only the females have the sting. So in some sense, the males often still have the yellow and black stripy pattern. So in some sense, the males are Batesian mimics on the females. The males are actually harmless, the females are not. And I do wonder if that is why in some of these bee groups, most of the activity through the year, most of the building the hive is done by females, and the males come out late and are therefore, at least in time and probably in number, only a small fraction of the bees. So I wonder if that imbalance in the sex ratio is partly driven by this mimicry effect, that if you had too many more males, they would destroy or disrupt the signalling, and therefore the male numbers want to be small. But that is me speculating a little bit. But just to recap, we've talked about mimicry. This is where groups of insects look like each other, and we've talked about a couple of types of mimicry so far. We've talked about Mullerian mimicry, honest mimicry, where things that have defense mechanisms are under good evolutionary pressure, good selective pressure to all form the similar pattern to warn that they are dangerous. And they all benefit from that pattern, from each other. And therefore you can have large numbers of the groups of these insects. And they are giving that message. We've talked also about Batesian mimicry. And this is where something that is itself harmless and therefore hasn't had to invest biological resources in producing a defense uses the same color pattern as something that is harmful. And that tends to result in a situation where the harmless mimic can't become too common relative to the thing it's pretending to be, because if it becomes too common, that signal's no longer really working for predators. It's no longer really telling them, avoid this, it's dangerous. So that type of mimicry, you tend to be a bit less, you tend to be the less frequent insects are the models. They can still be pretty numerous, particularly with this sort of black and yellow patternation we've been talking about, because there are a lot of stinging bees. So you can have quite a lot of harmless mimics before you start messing up the message to predators. But the basic principle is there that generally you can't be too common. So we'll come now to another living specimen. Just open this box up. And I wonder how well behaved this is going to be. So what we've got down here, I think I might move over to where the light is a bit better, because it's not very bright in here. We have some technical difficulties, so we haven't got the power supply just at the moment. But what you've got here is a caterpillar of a moth called the blood vein. I haven't got its scientific name written down at the moment. And you might be able to see that's sort of reared up its front end in a way and has a pattern on it that, with not too much imagination, looks rather like a snake's head. And it's got this rather snake-like posture, holding its head up as if it's going to sting. It's going to bite something. Still focusing on wasps, you see, stinging, as if it's going to bite something. So this is thought to be a snake mimic. It's pretending to be a snake to defend itself. Now, there's a few things about this thing's mimicry. If you put my finger next to it to give you a sense of scale, that's not a big snake. You know, there aren't really any snakes apart from baby ones that are that size. So that's a bit odd. And this is, I'm broadcasting here from the United Kingdom. We don't have many species of snake. We have 3. They're not particularly super common, and none of them really are predators or threats to the sort of things that might want to eat this caterpillar. So that being the case, that feels really odd because this moth is pretty common and there are plenty of others that do this snake mimicry as well. And they are much more common. They are now much more common. I'll take this background here. Than the thing they're pretending to be, at least here in the UK. They're much more common than snakes. And that might feel a bit odd because what I said before was the things that are harmless but are pretending to be something harmful, they should be less common than the thing they're mimicking. But these caterpillars that look snake-like, certainly here and probably in a lot of the world, can be much more common than the things they're mimicking. So that feels like a bit of a contradiction to what we were saying before, that if you're a cheat, if you're one that's pretending to be something but being harmless yourself, there's a real pressure on them that stops them becoming too common, because then things will learn that it's not worth avoiding the signal. And that word learn, I think, is the key word here. That's the thinking as to why this is really possible to have these things being much more common than the thing they are mimicking, in a way that the wasp mimics, the bee mimics we were looking at before, really can't get away with, is that for a lot of things that are avoiding snakes, that avoidance of snakes seems to be hardwired into them, seems to be evolved into them. It's not a learned behavior. So if you're a little bird and you are somewhere where there are snakes, you don't get to go up to a snake and learn, oh, that was a bad idea, I'll not do that again, because you've been eaten. So it's not really a learned behavior on behalf of the predators. It's an evolved behavior. It's an intrinsic fear of snakes. And it seems that it's quite a strongly hardwired avoidance, because even quite poor snake mimics, and this caterpillar, I doubt many of us, after more than a fairly superficial glance at this caterpillar here, would think, oh yes, I'm looking at a snake there. So the mimicry isn't necessarily brilliant in that, but it nevertheless is there. And because the thinking is, because it is an intrinsic need to avoid snakes that various predators have, they will just avoid that without needing to learn it. So this doesn't need to worry about being less common than the thing it's mimicking, because there's no learning going on. So there's no chance that even if there's loads and loads of them, at least in the short term, that the predators will learn, oh, it's actually worth having a go at that snake thing. It might be tasty. So you can get this mimicry going on where the mimicry is more common I think it probably does count as a form of Batesian mimicry, but you don't get the pressure restricting the numbers in the way we did with the things we were talking about before. And you might think, well, that's fine, David, but you said earlier that, you know, in the United Kingdom where you're broadcasting from, there really aren't any snakes that are a problem for the sort of things that might be wanting to eat those caterpillars. So why have they evolved? Why have they evolved to avoid snakes at all? It's not really a problem for them in Britain. They're not going to get eaten by snakes. We don't have things that predate on birds and mice and so on in quite the same way. So why have they evolved that way? And the thinking here is that it may well be that that's because we have quite a few migratory birds that might come here and spend their summer here and breed here in the United Kingdom. And there are lots of them that do that. But they spend their winters somewhere else. They spend their winters in Africa. It's quite a common place for birds that migrate to Britain to spend winter. So they spend winter in Africa where it's warmer. And of course in Africa, there are lots of snakes that can be a problem to birds. So that selective pressure to have an intrinsic avoidance of snake-like things is baked into the birds. And that means that, oddly, with some of these caterpillars that are mimicking snakes, they are mimicking snakes from an entirely different continent from the continent in which they are living. And they're mimicking snakes that they've never seen. It's all being done by the selective pressure of evolution. There's no great caterpillar school where they get a book of snakes out and look it up and decide who they're going to look like. Just selective pressure, the ones that looked a bit more snake-like, gave the birds, the mammals, particularly the birds, I suspect will be the ones driving this one, gave the birds a bit of a pause, and they had a bit more time to eat, to get away, to get to the next stage in their lives and breed. And the ones that looked a bit more snake-like did that a bit better, and they evolved and they were more and more snake-like. And that means you get, oddly, the appearance and patternation of snakes in Africa determining the appearance and patternation of caterpillars here in the United Kingdom, which I think is just amazing. So that's probably all I was going to quickly go through now, a bit of discussion of mimicry, a bit of discussion of how things look like one another, and show a few examples. And then if you are interested in some of this mimicry stuff, and particularly this discussion of snake mimicry, again, I'll show you this book. This is well worth picking up. Field Guide to Caterpillars of Great Britain and Ireland by Barry Henwood and Phil Sterling. And they go into this in much more detail in here, and even more detail in an article in a recent edition of British Wildlife magazine. And they discuss this snake mimicry a lot more than I do, and have some really good examples. So it is well worth, if you've got the spare money, picking up a copy of this book, just to read it, even if you're never going to try and identify a caterpillar in the field. But you should also go out and try and identify caterpillars in the field. So there we go. Mimicry in insects. We have things that are genuinely harmful and that tend to therefore have a similar pattern. Black and yellow in this case to say, I'm harmful, stay away from me. We have things that aren't harmful but try to have a similar colour pattern to give a similar warning. And they tend to not be able to be too common relative to the things they're mimicking, because the predators won't learn to avoid those patterns if those patterns are too often on the harmless things. And then we've got a few things, this caterpillar mimicking a snake is one of them, that is mimicking something whilst being harmless itself, but because the avoidance of the thing it's mimicking is intrinsic rather than learned, can be much more common than the model. So I think we'll end on the picture of this caterpillar. I hope people found that interesting. And there are lots of other ways, of course, insects defend themselves, and we may talk about some of them. in other broadcasts, and we may go out in the field and try and find some of them. But for today, I'm going to sign off now. Thanks.